The YouTuber My World Is Mine 72 asked me if I'd do a video on the 555 timer. So I got out my Heathkit, Zenith Heathkit trainer, looked through some boxes, and here you can see that I found a 555 timer. Here's a drawing of that 555 timer. Pin 1 is ground, 2 is the trigger, 3 is the output, 4 is reset, 5 is a control voltage, 6 is threshold, 7 is discharge, and 8 is the positive voltage, running somewhere from about 5 volts up to about 18. Now, this particular chip that I use is marked with a dot telling me where pin 1 is, or which end of the chip is, basically. But sometimes it'll be configured like this. There'll actually be a notch at one end. But anyway, it will be marked. There is a link in the more information of this video to the PDF of the 555 timer. And there's lots of information there, and this is one of the drawings. It's this drawing and the next one down in that PDF file that you might want to take a look at. This drawing here, this block diagram, is very useful, and I used it along with the next drawing in the PDF file to get the information I need of some of the things that makes this 555 timer operate. The first thing that I keyed in on was those 3 resistors. It goes from the positive power through 3 resistors to ground, and I did find them in the next diagram in that PDF file. It's a whole bunch of transistors. And to help you find it, the values of those resistors are this: 75K, 5K, and 5K. But what's really interesting about this drawing is, from the names, sometimes you don't really understand what these things do, like threshold and trigger. Kind of understand the trigger part, but what is threshold? Well, looking at the block diagram, they're both comparators. They are separated by a resistor in this simple block diagram, but basically it's a comparator. And take a look at what each of them do. Each of them supplies an input to the flip-flop, and that might seem a little strange. Now, the flip-flop is a circuit where you have, in this case, it'll be 2 transistors, and one will be on and the other one's off, and vice versa. So I use this block diagram and the large drawing of all the transistors to figure out a few things that will be useful. And looking at that diagram after this one, what I found out was the threshold is Q1, and it is an NPN transistor. And the trigger is a PNP, and it is Q10, and the discharge is a NPN transistor, Q14. Well, what's important about that is the threshold requires an input of positive for that NPN. And for the trigger, it requires an input of negative for that PNP. Now that's some useful information. Now the discharge, all that is a transistor, and you can use that transistor any way that you want, and it is driven with the output of that flip-flop. So take the time to take a look at that information, and you'll see how I came up with this information. But before I leave this drawing, I want to point out that the threshold and the trigger, they're both comparators, and both are driving the flip-flop. Now from a website, which I also supplied a link, and there's lots of them out there, I'm just picking one of them, I decided I'd build this circuit, but I have modified it to this because I've got a 12-volt supply. So I upped the resistors on the right to 330 ohms. And I also added a variable resistor on the left side, and I added more capacitance on the left side. The resistors and capacitors on the left side of this circuit in this diagram make up an RC time constant, and in this video I have an analog meter hooked across the capacitance. Now I've got all the capacitance and the highest resistance as this video is running, and you can see that the capacitors charge up to a point, then the flip-flop flips and then discharges to a point, and it flips back again and starts charging the capacitors up to a point, and then back and forth, back and forth. If we would like to increase the number of times it changes from red to green and vice versa, there's a few ways we can do that. And in this video, what I'm going to do is first lower the resistance of that 100k ohm resistor, and you'll notice that the time that it takes to flip between red and green is less. Also, now I'm putting the resistance back to 100k. If we take out the larger capacitor, that also will increase the speed at which it goes from red to green. And now if I also lower the resistance, it speeds up some more, and here it's so fast you can barely see it switching between red and green. Now there was another lead at pin 5, which is the control voltage, and what I'm going to do is I've got two 100 ohm resistors. One goes to ground and one goes to positive 12 volts, and I'm first going to touch pin 5 to ground, and we'll see what happens with the LEDs. And then I'm going to connect pin 5 to positive 12 volts. Okay, we've got the flip-flop running. Now I'm going to connect pin 5 to ground, and you can see it stopped on red. Now it's not connected. Now when I connect it to positive 12 volts, it's green. So ground makes it red and positive 12 volts makes it green. From the transistor drawing in that PDF file, we've got two transistors in the output driven by the flip-flop, Q22 and Q24. And this is how the diodes can light, one green and one red. If we got a positive voltage that turns on Q22, now you can only Q22 can conduct, or 24. You can't have both, and they both cannot be off. It's one or the other. So we got a positive voltage on the base of 22, so it is going to conduct. And here is the current flow through the 330 ohm resistor at the bottom, through the green diode, through Q22, up to positive 12 volts. Now if we had a positive voltage on Q24 that causes it to conduct, we'll have current running through Q24 through the red diode up through the 330 ohm resistor to positive 12 volts. There's a lot of good information in that PDF file. Also, there's a lot of nice circuits to build on that website. Thanks for watching.